Well, so we were solving this the second problem in the last class. Part A we already solved, and now we'll go for the part 2. So now path has been changed. Path of the integral has been changed. Yeah, so in part A we were moving from the point 0, 0, 0 to the point 1, 1, 1, following the curve x is equal to t, y is equal to t squared, z is equal to t cube. Now in part B we are moving from the origin to the point 1, 1, 1 following a different line. So from 0, 0, 0 to 1, 0, 0 and then 1, 1, 0 and then finally we'll move to 1, 1, 1. So let us draw the path. So path has been changed. Let's see if the value of the integral remains same or not. So this is my coordinate system. 0 x z y. Now we are starting from the point 0, 0, 0. This is the starting point, and then from there we are moving to the point say A having coordinates 1, 0, 0. Then this is the first part of the path, and then from there we are moving to the point 1, 1, 0. This is in the xy plane, say B. And next we are moving to the point C 1, 1, 1. So therefore, essentially we are moving from 0 to A to B, and B to C. And we have to find the line integral for this particular path. So therefore, C, the path, say gamma is given by gamma is equal to OA plus AB plus BC is the entire path. So therefore line integral, so this is the equation 3x square plus, this is the vector field 3x square plus 6y I. Okay, so you tell me the vector, so I will write, so 3x square plus 6y minus 14yz j plus 20xz square k. Okay, so if this vector field is equal to 6x square plus
No, sir,
6
3x square.
3x square
Sir,
plus
3x
6y.
square plus 6y.
3x square plus 6y. Okay, 3x square plus 6y I minus 14yz
By
JK
JK.
is
plus
plus,
20
Plus
square
20
KK.
xz square.
yeah, so this is the vector field, and therefore this line integral over the curve gamma f dot dr, this is equal to O A f dot dr plus AB f dot dr plus BC f dot dr. The entire integral can be decomposed into three parts. Now on OA we are moving on the on the x-axis, and there coordinates of y and z are not changing. So therefore dy dz is equal to 0. So on OA, dy equal to dz, that is equal to 0. So therefore OA f dot dr, so which is equal to OA 3x square plus 6y dx plus in fact minus 14yz dy plus 20 zx square dz, zx square or
No, sir.
xz
X
square,
Z squared, sir.
xz square.
x square, sir.
The
Okay.
dy dz 0 na, sir.
So dy dz, still I am writing in the first step. Since dy dz 0, so it will become 0 to 1. X is changing from 0 to 1, and y is also 0. Note that y is also 0, and z is also 0 as we are moving on the x-axis. So therefore, it turns out that we get dx, and this is equal to 1. So this is 1, and now on AB, f dot dr, this is equal to, once again, let me write 3x square plus 6y dx minus 14yz dy plus 20 xz square dz. Now let us look at the graph. As we are moving on the line segment AB, so which coordinate is changing?
So dy
X.
dz is equal to 0,
Y.
but y is equal to some value.
So x remains 1, you see. X remains
Yes, sir.
1,
Z
Yes, sir. Dx and dz will be 0.
dx is 0, only
X
y
remains
is
1 and
varying.
y 0 to 1.
0 to 1.
Yeah. So on AB,
X equals to
on AB, x is always 1
1
and y is changing, z is also
Z
0.
0.
And therefore dx, since x is constant, dx and dz
0.
both are
0.
0.
Both are 0.
0.
So, yeah, and y will vary from 0 to 1. So therefore, we are left with only this term, minus 14 yz.
Sir,
And
0 na, sir. Z is equal
if
to
we
0 na,
put 0, z is equal to 0, then
all
we
0,
will
sir.
get, so this is equal to 0.
All 0.
So
Yes.
if we plug all these information in this equation, we'll get 0. Okay, so now the last part. So what is the last part? BC f dot dr, this is equal to, on BC, 3x square plus 6y dx minus 14yz dy plus 20 xz square dz. And now let us look at the figure. So
Z
as
is
we
equal to
are
1.
moving,
0
only
to
z
1.
coordinate is changing. Okay,
Yes,
on
sir.
BC,
Equal to 1 and y is
x,
equal to 0.
x is equal to 1, y is also equal to 1 at this point. So this is 1, 1, 0.
dx dy is equal to 0.
My same na, sir.
And z is changing from 0 to 1. So let us use this information on BC. X is equal to y is equal to 1, dx equal to dy equal to 0,
0.
and dz will only be the term. Okay, and yeah, so therefore this will become
20 by
0
3,
to
sir.
0 to 1, 20 xz square. So a value of x is equal to 1, and
20 by
20 will be z square dz, right?
Yes,
And
sir.
this will be 1/3, so 20 by 3. So therefore, eventually,
23 by 3.
yeah, f dot dr, this line integral turns out to be equal to 1 plus 0 plus 20 by 3. This is equal to 23 by 3. Okay, so this is the solution. And now you can try the third problem. I am leaving it for you. We'll move
13
to
by
the
3, sir.
Hmm?
The C part is 13 by 3.
13 by 3. Okay, very good. And I can see there is a huge discussion in the chat group, and which is good. And if you have any query, I will be happy to answer you after the class. Okay, so for the time being, let us move on and introduce the concept of surface integrals. So in the surface integral, as I mentioned in the basic concept, that we need one region of integration. So what is the region of integration in this case? It is a surface in space, some kind of surface. It may be a portion of paraboloid, it may be a portion of ellipsoid, or it may be a portion of ellipse, or it may be a portion of a plane. Okay, so surface is a three-dimensional object in this case, and that is the region of integration. And what else we need? We need either a scalar function or a vector function defined on that region. So these are the two basic stuff to start with, as I mentioned earlier. Okay, you need a region of integration and a function. It may be a vector function or a scalar function. Okay, should be defined in that region. Then what is the basic procedure? So we'll divide the region into finite parts initially, small finite parts. And from each part we will consider a point. And at that point we will evaluate the function, be it vector or scalar, whatever be the case. We'll calculate that vector, and we use that vector or scalar to define our element. Okay, so that is the basic procedure. Now in this case, let us look at this figure. This is the region S. This surface S is the region in space. The surface, you can understand. So what is that? And A is the vector function. A is the vector function, and we will define this surface integral over a vector field. So A is the vector function and S is the surface. Surface is the S is the region of integration, and F is the relevant function for which we are trying to define surface integral. Then what we will do, we will divide this entire S into finite parts, and out of which a representative part is delta S. So which has been shown with this black rectangle type of region, small rectangle type of region over here. Now at this point we have to understand the positive normal, the concept of positive normal. It is basically a technical term. Positive, it depends actually. It depends on the user. Suppose we are considering a surface, um, say sphere or hemisphere. Then you can consider the outer normal to be a positive one, or inward normal to be a negative one. That is the normal convention. But if you consider the inward normal to be a positive one, then also the theory will absolutely work. Only thing is that whenever we will mention the related theorems, some of the theorems like Gauss theorem or Stokes theorem, Green's theorem, in those cases a specific orientation is necessary. But for defining surface integral, uh, the positive normal to an element, positive unit normal to an element, is purely user dependent. So in
Sir,
this
if it
particular,
is unbounded, then
in unbounded region, at this moment we are not defining the integral. So in that case we have to consider improper integrals. Okay, so at this moment we are considering bounded region, integration in the bounded region. And for unboundedness, as you have noticed, for defining alpha beta functions or improper integrals, what we did, we considered the limiting approach. Okay, so similar kind of approach may be applicable, but in this particular course all the surfaces and volumes we are considering are finite in nature. They are bounded in a finite portion of the space. Okay. Hmm. So now this is your S, and as I mentioned earlier that we will divide this region into finite parts, and delta S is a representative part. It is taken at a point PP, capital PP, and the outward normal or positive normal is taken in this direction. And AP, if you calculate AP, PP is basically any point, a considered point inside this region delta SP. Okay, so at this point we have calculated the vector AP, and we have the normal, unit normal in this direction as shown in the picture. Now what you can do, you can define a scalar quantity by considering a component of AP along the normal direction. Okay, so then how you will get that component? You have to just take the dot product, since this is an unit vector, dot product of AP and NP. Note that AP is a vector and NP is a unit vector, unit normal vector. Okay, you just take the dot product, you will get a number. Okay, so that is the contribution of the function in the element. Then you multiply that number with the area of this element, delta SP. You remember the analogy, the integration element for one-dimensional functions of a single variable, the integration element has been f of a plus RH into H. Okay, f of a plus RH, that is the contribution of the function into the length of the element. And in this case, what we are doing, we have a vector function associated with the integral, and we are taking the value of that vector function at a particular point within the element, and then we are taking the normal component of it, and then that is the contribution of the function, and then we are multiplying that function, number with this delta S. This is our integration element, and we are doing this, we are calculating this element for each and every elements into which we have divided the surface area S, and then we are forming the sum. Here you see, this is the contribution of the function A, xp, yp, zp, that is the coordinates of the point pp, and then we are taking the normal component of that vector. We will get a scalar, and that scalar is multiplied with delta S. Okay, that scalar is multiplied with delta S, and that is my integration element, and we are forming the sum over all such elements starting from p equal to 1 to capital N. Okay, so if the limit of this sum exists as delta SP tends to 0, that means we are considering more and more number of smaller elements. If this limit exists uniquely as n tends to infinity, then this limit is called the surface integral of the vector field A over the surface S. Okay, so this is the definition. Now you look at this delta S, this differential element. So for finding or for evaluating this surface integral, this delta S might create problem. So therefore, how to convert this delta S or ds to an appropriate Cartesian differential? So let me check if I have the figure. So where is the figure? Yeah. So what we do, we project. Let us suppose the projection of this S on xy plane. Note that this projection is only allowed when this projection is 1 to 1. That means any point of S is projected to a single point on R. This projection is 1 to 1. That type of projection is allowed. For example, if you are considering a sphere over here, then 2 points will be projected to a single point on the xy plane. Then that type of projection is not allowed. Then you have to look for another appropriate plane where the projection is 1 to 1. So we have to be careful about that. But in this case, the kind of configuration we have taken over here, we have absolutely no problem. So then delta S, let us project this delta S on xy plane. So entire surface S is projected to the region R on the xy plane, and then you project this delta S on XY plane. You will get an element, and let us assume, without loss of generality, we can assume that this is rectangular in nature. We can design the surface elements on S in such a way its projection on the XY plane is a rectangular one. So that we can do, and uh, with dimensions delta X and delta Y. So this projection has dimensions delta X and delta Y, or length delta X and delta Y in the along the X as and Y direction. Okay, so then what is the area? This area is delta X delta Y, delta XP delta YP. And what is the relation between these two surfaces, delta S and this delta X delta Y? So let us have a look at it. Approximately the situation is something like this. Yeah.
Sir,
So
what was the AP here? AP vector?
AP vector is the constant vector
Vector
calculated
function.
at the point PP, whose coordinates are XP, YP, ZP. AP is basically, this vector is the vector A calculated at this point, ZP, right?
So PP is a point on SP.
Okay, sir.
This PP is a point in the element, delta
Okay.
S, this element. Okay. Now you have a situation something like this. This is the rectangle on XY plane, and if you move this delta S parallelly along this shaded region, then you will have this kind of situation. Although if your region delta SP is very small, you can approximately think that this is a kind of rectangular thing. Okay, so this is your delta S, delta SP, and this angle is theta. How to determine this angle? This is simply given by this K.
Dot product.
Dot product of the unit vector
Yes, sir.
N and NP, right? NP and K. Okay, so therefore, if this angle is theta, then delta XP, delta YP, this will be equal to, okay. So let me write it in
Divided
this,
by.
K
divided
is
by
also
cos
a
theta.
unit vector, sir.
Which one? K. Yeah.
Yes, sir.
NP is the unit vector. K is also unit vector. K is the unit vector on the XY plane.
Yes, sir. Yes.
Okay, so delta SP, will
Cos
be
theta.
equal to delta XP delta YP divided by cos theta,
Cos
First,
theta.
and this is equal to delta XP delta YP divided by mod of N dot K.
yes, sir.
Okay, it may be negative actually. It depends on the user. So instead of considering this NP in this direction, we could have taken NP in the reverse direction. In that case, we would have got this N dot K negative number. So therefore, we have to take this mod. Okay, because delta S is a absolute number, and we have to connect in this way. Okay, so you see, then this ds can be converted to this differential if we are allowed to take the projection on XY plane. Okay, so ds, this evaluation of this we don't know, but once we have the differential in this form, dx dy divided by some number mod of N dot K, you will get some number over there or some function over there. Then basically we have a double integral, and I think all of you have learned how to evaluate a double integral. So therefore,
We can actually substitute it with dy dz also by using I cap vector.
yeah, so in that case you have to involve the either you have to involve the I cap means YZ plane. You have to take the projection on YZ
Yes,
plane.
sir.
Okay, it
Yes, sir.
depends on the problem or the surface you are
Means
considering.
it
Where
depends
we
on
get
projection also,
a
no, sir.
single point or rectangular form. Sir,
Please.
on which plane we get the single point or rectangular form, we have to take that.
Rectangular form, you can do it actually. If you think little bit, suppose you have a curved surface, but you can design your element. There is no restriction on the shape of the element to be taken on the surface. Okay, that is in your hand. So any type of shape, only thing is that this should converge as n tends to infinity. Okay, so it is independent of the choice of the shape.
Sir, I couldn't understand the projection in 1-to-1, sir. What is written over there? Sir,
Okay,
if the
so
set project is
okay, so
not one.
let me give you one example. Suppose you have a cylinder. Okay, suppose you have a cylinder, something like this. You have a cylinder. So this is your S. The outer surface of a cylinder is your S. Now you want to find the surface integral on the surface of the cylinder. Then if you project it, the kind of orientation we have take, if you project it on XY plane, then uh, corresponding to each line on the generator, you will get a single point on the XY plane. You understand? All the lines will be projected. This is the normal orthogonal projection, right? So all the lines over there will be projected to a single point. That means this is infinity to one projection.
Okay.
Okay, so then it is not valid. But if you take a surface something like this, so only one point will be projected to a point. This is allowed.
Okay, sir.
Okay, so it depends on the theory actually. I am not getting so why this does not work, and so all these theories are yeah, quite extended actually, and yeah, we don't have much scope to discuss all these things. But working rule is that while taking the projection, we have to be a little bit careful. Okay.
So what is K cap?
K cap is the unit vector in the direction of z axis, because we are projecting on the r plane, xy plane. So what is its normal vector? Its normal vector is k cap. Okay. So we are taking the dot
Sir,
product
how
of the.
did we determine the n vector over here?
Please repeat.
Gradient, using gradient,
Yeah,
finding
if
invariant
surface is
vector.
normally given, equation of the surface will be given. When I will solve the problem, you will see. Then you use the gradient. Okay, and if you find the gradient, then divide it by its absolute value, you will get the unit vector. Okay.
And sir, for example, if we had to find the double integral for a shape like a cone, how would we take the element in that case?
The equation will be given for the cone.
No, I don't understand. Don't get your question. So if the surface, your question is if the surface is a cone.
Yes, sir. Then
Yes, sir.
how we take the delta S?
Yes, yes.
Yeah, so you can design. So no problem. So suppose this is your cone. So you can take something like this, or it will definitely have some curvature, but you can change the orientation a little bit so that
So
it
we
is
can
approximate.
project it along any plane, that is x, y, y, z, z,
Sir,
x,
but
No,
y,
the
no,
z.
no. Here if it depends on
because
the axis.
very small.
If it is
Curvature
this
will
is
be
your
negligible.
axis, then
In
you
x,
have
y
to
plane,
project
sir.
on only xy
Base.
plane. Otherwise, at least 2 point will be projected to a single one. Okay, so then
But the curvature is negligible, na, because we are taking so small area,
yeah,
dx dy. So
curvature
it
is
can.
negligible here. That is why this approximation is quite intuitively one can understand that it can be projected to a rectangular area on an appropriate plane. Curvature is negligible. If you look at locally, it is something like a plane. Okay. Yeah, so there is another type. So I have mentioned something in the bracket. This is also very important. Surface integral of a vector field, and it is also called normal flux of the vector field over a surface. Okay, so this surface integral is called the surface integral we have defined over here, this one is called the normal flux of A, of the vector field A across S. For example, if this A is equal to the velocity field in a fluid system, then what does this represent? Do you have any idea? If A is a, say, vector velocity field, A is a velocity field and S is something like this. S is something like this, and you are considering normal in this direction, let us suppose. Then this vector, this surface integral, basically, which is also called
Velocity
the,
profile.
yeah, if A is equal to, basically, let us suppose V. Then what we will get? We'll get as V dot dr, ds, V dot n ds. So what is the physical significance? If V is the velocity of the fluid particles in a fluid system, then what is the physical significance of this?
So the continuity equation, sir.
Yeah, continuity
Constant.
equation
Yeah,
will come, but this is the volume of
Or
fluid
the
which is
velocity at a
crossing.
point.
the
So
amount
let
of
us
Determine.
find.
fluid passing through that
This is the
area.
volume of the fluid. You see, velocity. This is the volume of the fluid which is crossing the surfaces per unit
Yes,
time
yes.
from one side, from the negative side of the surface to the positive side. Okay, positive side is determined by this normal vector. So therefore, although it is defined mathematically using the limit and its existence, as soon as you replace this vector with some relevant physical quantity, accordingly, the meaning of this surface integral will be assigned. Okay, so
Sir,
this
one
is
other
one.
example is Gauss theorem that we have for
Sir,
electricity.
can we use partial
E dot
derivative to find cos phi,
E
cos
dot
theta?
that we have. That is
Partial
also
derivative is not necessary. You have simply two vectors, two unit vectors, and normal to the surfaces, and you want to determine the angle between the surfaces. So then simply take the dot product.
Okay, sir.
Okay, so so this is very useful, and later you will you have to read probably in different subjects, there are different branches, the transport phenomena, heat transport, momentum transport, mass transport, etc. So there, this flux, this surface integral will be very much useful. Okay, especially I am aware that in mechanical, chemical, and up to certain extent in metallurgy also. So you will be using this quantity frequently. Okay, other subjects I am not that much aware, but the concept of this transport or flux is very much important. So that I can say, yeah. So instead of a vector function, if you have a scalar function defined in that region, in that surface S, then similarly, we can define surface integral involving this scalar field. So how we can do this? So once again, same approach, we will divide the region of integration, which is the surface portion, finite portion or bounded portion of a surface, divide into finite parts, and one such part is delta sp, whose area is delta sp, and at that region, tiny region into which the entire surface is divided, we consider a point, and there we will calculate the value of the function. This is the contribution of the function, and that value is multiplied by delta s. That value is multiplied by delta s. This is your integration element, and then you take the sum and finally take the limit. And if this limit exists, it is called the surface integral of this function phi across over the surface S. Okay. Similarly, this ds we have to replace. If the projection on xy plane is allowed, we have to evaluate this using a double integral using the projection. Note that this surface S is projected to the region R, and this ds is replaced by dx dy upon n dot k. This will give us cos theta. And note that this function is a yes.
Sir, you said that when we are converting from delta SP to any of the, if we try to project it either on the XY plane or the YZ or the ZX plane, will we get always the same answer for the double integral? Even if suppose it was like if the projection gave a line, suppose, so always it will
If
give
the
the same
projection
value
is
for the double.
allowed, always you will get same result irrespective of your projection plane. Okay, you will get the same result. And one important point, this phi is a function of x, y, and z. This phi, and we have converted it to a double integral on xy plane. So note that we are evaluating this phi, this surface integral on the on a surface whose equation is given. If it is a plane, then it will have an equation of the form ax plus by plus cz is equal to d, or plus d equal to 0. Then as we are evaluating this function on the surface, then z we can replace by a function of xy using the equation of the surface. Okay, I will demonstrate with examples. Okay, so this is the thing, and then eventually this phi will be a function of xy, phi, and this contribution n dot k will be a function of xy, and we have a perfectly nice double integral, and we know how to solve it. Okay, so now I think we are in a position to acha. So now in particular, this, if this phi is equal to 1, what you will get? What is the physical significance? So what you will get over here if you
So the
calculate the
projection, sorry,
Sir,
sir. So the
volume
area
Area.
of the
we will get.
surface,
area
area of
of
the
the
surface,
surface?
sir.
Very good.
Area of the
Because this is,
Area.
in that case, this phi is equal to 1 means you look at the sum. These are the sums of the elementary areas. So you will get the area of the surface. Okay, so using
Yes,
this
yes.
surface integral, sometimes we evaluate the area of complicated surfaces. Okay, and yeah, so if the equation of the surface you see is this, equation of the surface is given by z is equal to some function of xy, then what is your normal vector? Normal vector n.
Grad of phi.
So no,
Grad
unit
n.
normal means you have to grad of phi divided by its modulus. You look at this term.
Yes, sir.
Yes.
So this is your normal vector, grad of phi, a grad of f. Yeah, I did some mistake over here. This is not your f. F is function of xy. Z minus fxy. That is your. I should have written phi over here, where phi is equal to z
Z minus.
fxy minus z. So you understand my mistake over here?
Yes, sir. Yes, sir. Yes, sir.
Okay, so then what is your grad phi? Grad phi is equal to, we know that we have to differentiate phi with respect to x. So grad phi is equal to I del f del x. Z will not have any contribution, plus j del f del y minus k. This is your grad phi. And if you divide it by its modulus, you will get this thing in the denominator. And if you take the dot product of
Don't
this
take
with
it.
k, you will get absolutely this one.
Sir.
Okay.
Sir, why does Z have no contribution here?
There is
Yeah,
minus
this
one now.
one, this one.
Partial derivative. It's a partial derivative. So
Yeah, so we have to differentiate it with respect
Z
to
will be
x.
constant.
Z
Okay.
is constant, so it will not contribute. Okay, you understand?
Yes, sir.
Someone is moving in a bus probably.
Sir, why that minus k has come?
Achha, so
Yes, sir.
let me.
It should be -1, I think.
No,
There
no,
is more than
magnitude,
minus.
magnitude. That is magnitude. Just a minute. Let me explain. So what is the magnitude of grad phi? This is equal to root over del f del x whole square plus del f del y whole square plus -1 whole square. Okay, so this is the magnitude, and we are dividing this grad phi with its magnitude to get the unit normal. Right, so therefore this +1 is appearing over here. Do you understand? If you take
Yes,
the
yes.
divided this, and then you have to take the and
Dot
then
K
here,
vector.
yeah, with dot and then absolute value. Absolute value will give you, instead of -1, you will get it like 1. And then you replace this ds by this. You plug this value in the denominator, and you will get this one. Okay, so this is the working formula, and now we can demonstrate with examples. So evaluate this surface integral, and where what is your s? S is the part of the plane which is located in the first octant. Located in the first octant. Okay, so first we have to clearly understand the surface S, which is a portion of the plane. And let me draw this. 2x plus 3y plus 6z is equal to 12. Okay. So how much time do I have? Okay, I can solve this problem. 2x plus 3y plus 6z equal to 12. So what is the equation? 2x plus 3y plus 6z equal to 12.
12.
This is my equation. And let us take it in intercept form. This is by 6 plus y by 4 plus z by 2 equal to 1. So this is my coordinate system, and 0. This is 1 point. Let us suppose 6, 0, 0. And y-axis is intercepted at the point 0, 4, 0.
0, 4, 0.
And 0, 0, 2.
Yes,
0,
sir.
0, 2. 0, 2. So this is say A, B, C. And we have to consider this portion of the plane. It's not good. And then, yeah. So you can visualize the thing. 0x, this is my x-axis, y-axis, and this is z-axis. Okay. And now what is the projection of this region on xy plane is allowed?
Yes, sir.
Yes,
Yes,
sir.
it is
Yes.
allowed. Let us
6
look
by
at the
7.
projection.
Cos
Let
theta
us
is
look
6
at
by
the
7.
projection. Yeah, this is your R, projection is R. And let us explicitly look at this projection. This is your 0, 4, 0, and not 0, yeah, so control Z. So we are on XY plane now, 0, X, Y. So what is this point?
6, 0.
What are these?
4,
6
0
0 0
and
6,
0,
0, 6.
Yes, sir.
6,
0, 0.
0,
yes, sir.
and
0,
0 4 0
0, 4,
0,
0.
0, 4.
Yes, sir.
We are on the XY plane. This is my R. And what is the equation of this straight line? You have to just set Z off.
X
X
by
by
6
6
plus y by
plus
4.
y by 4 equal to 1. This is your equation. Now this is the region. Okay. Now from this equation we have further information. We will write 6z is equal to 12 minus 2x minus 3y. This we will use later on. Now let us focus on the double integral, surface integral. On S, this is your S. This one is your S. F dot no, not control Z. F dot N ds. And n, what is this n? N is the unit
K
normal
cap.
to the plane.
Sir, sir.
To the plane.
Yes, sir.
And this is equal to, so what is your n? So this is the plane. Immediately you can tell me the unit vector.
2i cap
2i
plus 3j cap
plus
plus
6j cap.
6k cap by 7.
Yes, sir.
2y plus
Yes.
3j plus 6k.
6k by
6k
7.
by 7. Yeah. This is the n cap. And what
Yes.
is your f? Tell me. Do you remember f, or I should?
No, sir, it was very big.
Okay, so let me just have a look at it. 18 Jedi minus 12J plus 3Y. 18 Jedi, someone of you please write it down and tell me. 18 Jedi minus 12J plus 3YK.
Okay, sir. Today.
18 Jedi minus 12J
12J
plus
Plus 3y.
3YK cap.
3y cap.
3YK.
3y
Yes,
k.
sir.
Yes, sir.
Yes, sir.
Okay. So therefore, if you take the dot product of this with the unit vector, you will get basically, first of all, 1 by 7 will come out. Yes, f dot n will be given by 36z minus 36 plus 18y ds, right? Dot product. This f with
Yes, sir.
n, this is your n.
Yes, sir.
So this is my dot product, and then we will change this ds as well as this z. As I mentioned in the comment that this phi, the function phi
It will be
involved,
0.
no, not z equal to 0. We are evaluating it
XY
on
plane,
the
sir. No,
s.
12 minus
anything
3
XY.
by
So we
6.
have to use the equation of the surface
Yes,
to
sir.
replace z. 6z is
I
equal to
guess, sir.
12 minus 2x minus 3y.
Y.
Yeah, 1 by 7, and then we will consider it r. R is the projection of s on the xy plane. Okay, so this is your r, and this 36z will be this will be multiplied by 6. 72 minus
12x
12x minus 18y,
18.
and
Sir,
minus 36 plus 18y.
sir, 24
Yes.
answer, sir. 24.
Answer?
Yes, sir.
Yes, correct. Very good. 24 is the answer.
Sir,
And dx dy, ds will be replaced by, and what is your n dot k? This is equal to
6 by 7.
6 by
So
yes, sir.
6 by 7, right? So now you have to tell me the simplified form. 36 18y is cancelled. 36 minus 12x,
12x.
and
Yes,
this
sir.
6
will be 1 by
minus
6.
6
2x.
common, sir.
So 1 by 6 will come from this n dot k.
Yes, sir.
1 by 6, 7 will be cancelled. Okay, this 7. So 1 by 6, let us now write, this is equal to 1 by 6 r. This is how much?
6 minus 2x, sir.
That's 6 minus 12
Minus
by
2x.
12x, and this is dx dy. This
Yes,
is my
6
double
common.
integration, and we can take 6 common.
6 minus 2x.
6 minus 2x dx dy.
dy.
Now once again, let me draw the region R on the xy plane, which is the projection. Okay, so this is your this region, and this is 60 and 04, and the equation of the line, this is your R, and equation of this line, 2x plus 3y equal to 12.
12. Yes, sir.
Yes, so therefore what we will do, so you know the
X
probably you
x
know
equal
how
to
to
0
evaluate
to
the
6.
double integral, how to
So
evaluate the
x
double
equal
integral.
to 0 to 6. Y is equal to 12 minus 2x by 3, sir.
Yes, very good. So So let me just repeat how to evaluate a double integral. You have a region of integration in a portion of the two-dimensional plane. And there are two possibilities. Either you can look at the region from the side of the x-axis, or you can look at the region from the side of y-axis.
Horizontal strip या vertical strip.
Yeah, so these are two ways of looking at that region. So whenever you look at this region from the side of x-axis, you look at the range of x, which is 0 to 6.
0 to 6.
And for each values of x, how y is varying, that we have to look at. So for example, this one. For a particular value of x in this region, y is varying from this curve, lower curve, that means x is equal to 0, y is equal to 0 to this line. The minimum value will lie on y is equal to 0, and the maximum value for each values of x will lie on this line. That means y is equal to basically 12 minus 2x by 3
By 3.
on this line.
By 3x.
No, 12 minus 2x by y is equal to 12 minus 2x by 3. So therefore, for each value of x in the range 0 to 6, y will vary from 0 to 12 minus 2x by 3. This is how we evaluate the system. Or alternatively, if you look at the region from the side of y-axis, what you will get, you will see that y is varying from 0 to 4. And for each values of y in this range, 0 to 4, x is varying from 0 to this line.
12 by 3.
12 minus 3x by 2.
12 minus 3y by 2.
3y, 12 minus 3y by 2.
3y by 2.
Yeah. And note that this region should be simply connected. If there is something like this, then you have to be careful.
Sir,
okay. Yeah.
in the previous slide, previous page, can you go, sir? Page number 5.
Here or in the
Yes,
note?
yes, sir. Sir, here at the bottom, sir, 72 minus 12, that part, how it comes, like I'm getting a little bit confused. Can you explain?
So this 6z is replaced by this equation.
Equal to
Multiplying
6z is
6z. 6 on both sides.
6 with
Okay.
Okay, got it. So you have to replace z, or you have to change z in terms of x and y using the equation of the surface, because we are evaluating on the surface. Okay. So therefore you are entitled to use the equation of it.
Sir, once explain that n dot k, sir, please.
N evaluation of n, did you understand?
N dot k, sir. Yeah, yes, sir, yes, sir. N is okay.
N is this vector. And what is your
Explain the
k?
evaluation.
This is k means 0 into I plus 0 into j plus 1 into k. You take the dot product of these two, you will get 6 by 7.
Sir, the evaluation of n.
Evaluation of n. You have to take the gradient. Actually, you have a plane. I thought you know. Anyway, so if you have a plane. So let me. So this integral I will discuss later on. So you have a plane something like this. 3y plus 6z is equal to 12, right? So what is your phi? What is the level surface? XYZ you can take as 2x plus 3y plus 6z. And this is basically a level surface defined by this function, scalar function. Now grad of phi you find. What is this? I del phi del x plus j del phi del y plus k del phi del z. This is equal to 2y plus 3j plus 6k. In fact, if you read or if you understand the equation of plane, general equation of plane,
Coefficient are normal.
the coefficients of x, y, and z, they basically give the normal vector. So immediately you can tell actually ai plus bj plus ck is the normal vector, and we need the unit normal. Therefore, we have to divide this nabla phi, grad phi, by its modulus nabla phi, and this is equal to 2y plus 3j plus 6k by its modulus root over 2 square plus 3 square plus 6 square. right? And you will get 49 here. So therefore 2i plus 3j plus 6k divided by 7. This is your unit vector. Okay. Now, yeah, so now we have to evaluate this double integral using repeated integral. So x will vary from 0 to 6. This we will evaluate later on, but before that, we'll evaluate y 0 to
4 minus 2 by 3x.
12 minus 2x by 3
By 3.
into 6 minus 2x dy. Note that while evaluating this integral with respect to y, we have to consider x to be constant. So therefore, 0 to 6, x equal to 0 to 6, you can just dx, you can take out 6 minus 2x and you will get
12 minus
y.
2x.
You will get basically y, and you have put the limit 12
12
minus
minus
2x by 3. So basically 12 minus 2x by 3 will come and 0 will not contribute. So 0 to 6, you have 6 minus 2x into 12 minus 2x by 3 dx, and 24 is the answer. You can now evaluate it.
Yes, sir.
Yes.
Okay, so today I don't have time. Do you have class after this?
Yes, sir. We have a
Yes,
class.
sir.
Yes, sir. We have
Yes, sir.
class.
Mechanics class.
Yes, sir.
Okay. So therefore, you keep trying. I have already uploaded this material today in the morning. Yeah.
Sir, in the previous class, you will be told that you will be provide some assignment.
Yes, sir.
Yeah,
You
I will
have said
provide. I
that.
have to prepare actually. So you solve these problems, whatever I have given at this
Sir,
moment.
assignment means we have to submit or we have to
No. That
for
is the
practice
assignment means
purpose.
you have to just for practice purpose.
Okay, sir. Thank you.
For practice.
Yes, sir.
Thank you, sir.
Okay, so
Sir,
thank
can you provide, sir,
yes.
sir, can you
Yeah.
provide answer keys of this exercise so that we
Yes,
can
sir.
verify that?
Answer,
Yes, sir.
I have to see. I have to work out the
Previous
problems.
question,
Yes,
sir.
sir. Answer is also important.
Yes, sir. Important.
Yeah.
Yes, sir.
Okay, I will provide
Yes, sir.
answers.
Okay, sir.
Most
Thank
of the
you, sir.
things I have most of the examples I have taken from Spiegel's book, and few problems I have taken from other material, other sources like internet and other books. Okay.
Sir, is the PDF available to you, like of the book? Do you have the PDF? If you have, can you?
Search it. I have the PDF, but I cannot officially forward it. I have the PDF.
Sir, one thing, sir, in this example only, while evaluating, sir, if we do it like you have done dy dx, but if we do dx dy, sir, then it is coming 0. Sir, why it is happening like that? Like the other repeated
First,
integral.
first you have
Limit
to
will be wrong.
first